So in this short video, I'm going to speak a little bit about the variance and standard deviation. I'll show you where the formula came from, and I'll build that up and share with you a couple of misconceptions that sometimes students have. Now, this short video is extremely important because everything I'm going to say is going to be very useful for you for the whole year. In most stat textbooks, if not all of them, you will never see where the formula came from. It's just given to you. It's just provided for you. So I wanna show you where it came from so you understand the logic behind it. Mathematicians tend to always build even definitions based on logical thinking. So I want you to follow this process of thinking. And for those of you who are or took calculus, I think you'll appreciate it even more. Okay, so imagine I have n observations. I call them x1 all the way through xn. The subscript just tells you the position of the observation. So we have n observations, maybe 20, maybe 80. I don't know what it is, but let's just call it n. So I'm just going to work with three numbers. I don't want to work with all of them. It takes time. So if let's say I have x1, x2, x3, and let's say they're put in order and they're in blue, and you find the mean, the arithmetic mean, which means x1 plus x2 plus x3 over 3, and it is x bar. So I just put it here in red. I don't know what it is. Let's just put it here. What we care about, as we discussed in previous videos, comparing the mean of this class to the mean of another class, to compare both classes is not sufficient. We need to talk about the spread or the deviation. And we discussed that the deviation is how far are these three observations away from x bar. So x1 is this much away from x bar, x2 is this much away from x bar, and x3 is this much away from x bar. Notice that this is negative. Of course, the distance is positive, but this is negative value, and this is a positive value. And that is a problem in itself. So imagine, I want to know how far these three data points are away from x bar, and I'm deliberately picking some nice numbers. Let's say I have -1, 0, and 1. I have n equals 3, just three numbers. I want to find x bar. Well, x bar is 0, right? -1 plus 0 plus 1 is 0. So how far is -1 away from x bar? It is 1 unit away. And how far is 0 away from x bar? It's 0 units away. It's literally on it. And how far is 1 away from x bar? It's 1 unit away. So if you use this idea, this is how it really started. We're going to take x1 minus x bar. We're going to add x2 to x bar minus x bar all the way to the last one. In other words, I'm going to do how far they are. We're going to take -1. We're going to take away the mean. And then we're going to take the second observation minus the mean. And then the third observation minus the mean. And we're going to divide that by 3. Isn't that what I'm trying to do here? Is that what I'm trying to do here, right? And if I do that, I'm going to get 0. So 0 means all of them are almost like sitting on each other. x1 and x2 and x3 are all sitting on 0, right? So this idea of figuring out the deviation x1, x2, xn away from x bar is very misleading, because that negative value might cancel a positive value. Look here, for instance. -1 minus 0 plus 0 minus 0 plus 1 minus 0. That's what I was trying to do here, right? You notice that this is -1 and this is 1. So they kind of cancel each other out. As if x1 was here and x2 was here and x3 was here, and therefore x bar was here as well. They're all sitting on each other, right? But that is not the case. This one is 1 unit away from the left, and this one is 1 unit away from the right. So this idea, the start is very good, but it's got screwed because this -1 canceled that one. So this is not a proper way to find the deviation of those values away from x bar. So somebody else said, okay, well, even though this is -1, why don't we just put bars? In other words, if I put a bar around this binomial, this will be 1, and this will be 0, and this will be 1 from here, right? And therefore, I will get 2 over 3. Well, that makes more sense. Because we don't care if the distance, if you are on the left or on the right. We want to put bars to show that this is 1 unit away from 0, and this is 1 unit away from 0. And I don't care if it is on the left or on the right. I need to make sure that we don't call this -1. We want to call it a distance of 1. So why don't we put bars around the binomials? So that is definitely a much better approach to the deviation than this one. And I put a cross in red again for another reason. For those of you who are or took calculus already, we know that functions like these, f of x equals, let's say, absolute value of x, we call these functions non-differentiable, right? They're continuous, but they're not differentiable. You know, there is a sharp corner at 0, and we don't like non-differentiable functions. Mathematicians like smooth curves. Smooth curves are continuous curves for sure, but they're also smooth. In other words, they don't have sharp corners, they don't have cusps, they don't have discontinuities, they're smooth curves, right? So we like differentiable functions because with differentiable functions, we can do a lot of mathematics. And when a function it has edges and cusps and corners, it creates problems from a mathematical perspective and in terms of creating models. So somebody else said, okay, well, I really want to make this 1, not -1. The bar didn't help because the function is non-differentiable. Why don't we square them now? Because -1 squared becomes 1, and 1 squared becomes 1, and that takes care of the bars. We don't need to deal with the bars. We know x squared is a nice smooth curve, right? X squared is a nice smooth curve, which means it's differentiable. It's very smooth at the bottom, by the way. So that's a better approach. And that's how mathematicians settled on the idea of the variance. They're looking for the spread or how are the values away from x bar. So they settled on this, but this in itself, even I put a green here, this is actually the definition of variance. That causes a completely different problem. And the problem is, this formula always gives you things in square units. So if, let's say we're dealing with points, or dollars or whatever, if you subtract dollars from dollars, you get dollars. Square the dollars, that dollar squared plus dollar squared is dollar squared. So this whole thing is in dollar squared, and that's just a naked number, has no units. So if these deal with dollar amounts, this formula called the variance is going to be something, you're going to write something like this, 106.57 square dollars, right? Well, that doesn't make sense because we don't like to work with, I don't even know what that means, square dollars, square points. So that's formula for the variance created an issue with the units. And for that reason, we ended up taking the square roots to resort back to something we really want. And that's what we call the standard deviation. So this is the definition of the variance. Now watch here. So the variance is exactly what I just said. You take the first observation, take away x bar, square it, and then you add second observation minus x bar squared all the way to the last one. X subscript n minus x bar squared, the whole thing over n. This is the variance. Now, if you don't like this notation because it's long, you can do a shorthand, right? Some of you have, I hope all of you have seen the summation notation. So it's just the summation notation of this expression. N doesn't change, right? N doesn't change. And all this means is I is an index. It's just a dummy variable. You're going to force I to be 1. You're going to have x1 minus x bar squared. Then you're going to add, and you let I jump to the next integer, which is 2. Then you get x2 minus x bar squared, and then add, and let I be 3. You get to here, and then all the way you get, you let I be n. You get x to the x subscript n minus x bar squared over n, which is this last one, okay? So don't get scared of this. This is just a shorthand of this formula. Now, we didn't care about the variance because, as I said, the unit doesn't make sense. So what we really care, and this is the mathematical expression that measures the spread or the deviation away from the mean. It's called the standard deviation. You can write SD of x. X is your variable, your random variable. Could be grades, could be heights, could be dollar amounts, whatever. So that's your variable. So the standard deviation of x is just the square roots of this stuff. Okay? So whatever you get here, put it underneath, take square roots, and you get the value. It makes sense because if this is in square dollars, this will be in dollars, right? If this is in square points, this will be points. Maybe you'll get 16.3 points or something of that sort. Now, I want to hit on two things that are very helpful, extremely helpful in this course. One is, there are a couple of ways to talk about the variance and the standard deviation. And it all depends on the context. When you are dealing with an entire population, the formula for the variance, VAR, we write sigma squared. This squared just reminds you that you're dealing with the variance. This is exactly this, okay? So there is no change between here and here. Just a notation. We write sigma squared of x, which is exactly this, which is this, right? And then, of course, the standard deviation, you just take square roots of this stuff, you get the answer. Exactly what I said here works here. When you are dealing with an entire population, and I'm going to explain this very clearly, okay? If you are working with a sample of the population, then things change a little bit. The denominator becomes n minus 1. It is the same thing, except this time you're going to divide by n minus 1 instead of n. And of course, the standard deviation of x is just the square roots of this stuff, okay? Once you get the variance, you get the standard deviation. Now, I'm going to explain to you what do we mean by sample and population and how the size can be very misleading. I'm going to put two things here for you. The size can be very misleading. And also, where does this n minus 1 come from? Okay? So, first, population means you didn't take a subset of whatever you're working on. For instance, last time we took the height of everyone in the class. That size was 15. Even though 15 is a small number, it's still the population. So don't let the number deceive you. Don't think this is referring to a population and this is referring to a sample. Oftentimes, the population might be actually small and the sample might be large. It depends on the context. So if I have a class of 15 students and I took their heights, which means I took a census. I asked everyone in the class, what is your height? And I recorded those numbers. That n was 15, and I was referring to the population, wasn't I? In that case, you divide by n. You live here. You don't live here. On the other hand, imagine I wanted to know the number of people who appreciate summer, like summer, in the US, and there are 340 million people. And I took a sample of 1,000 people. And hopefully I took a good sample, and we will address that issue later. Let's say I have 1,000 people in front of me who represent the entire population of the US of 340 million people. And I ask them, do you like summer or you don't, right? That n of 1,000, even though it is a large number, it is still a sample. And because it is a sample, when you find a variance and the standard deviation, you better divide by n minus 1, not n. So that is the very first thing I want to point out. Make sure you understand the context. Sometimes you are dealing with the population, and sometimes you are dealing with a sample. And don't let the size deceive you. That's the first point. The second point, why do we divide by n minus 1? And this is also not explained in your book, in most textbooks. Here is why. It has something to do with what we call degrees of freedom. Degrees of freedom. And this is something we're going to use the whole year, degrees of freedom, or as we abbreviate it by DF. DF. DF is N, and DF is N minus 1 for the sample, for this situation here. What is degrees of freedom? If I'm dealing with the entire population, let me work backwards. Imagine I have 20 students. Okay, that's my sample. I have 20 students, and I happen to know 19 of the students who are present. Wouldn't I be able to know the 20th one, even though the 20th one is not there in class? In other words, if I know n minus 1 out of the n, it is sufficient for me to know everybody. I'll put differently. Imagine I have, let me write here for you. Imagine I have 3 students, okay? And I gave them a test, and one got 80 and one got 90. So I have 3 students only. I'm only using a small number because I don't want to waste time. Okay? Now, I also know the average. So let's say the average is 82. Wouldn't I be able to know the score of the third one? Right? So you have 80 plus 90 plus the score of the third one divided by 3 is your X bar. So clearly I can cross multiply and figure out the value of the third score, right? In other words, if I just know 2, I have enough information to draw conclusions about all of them. So when you are dealing with a sample, your degrees of freedom is actually just n minus 1. You don't need to have n at your disposal. N minus 1 is sufficient. And by the way, sometimes we even use n minus 2. If I have one more additional information, as you will see in the future, let's say I have 2 pieces of information. I don't need to know n. I don't even need to know n minus 1. Sometimes we actually divide by n minus 2. And that's going to come in handy when we deal with residual. So right now, with one piece of information known, when you're dealing with a sample, you just divide by n minus 1. If you are dealing with the entire population, your degrees of freedom is n, not n minus 1. And therefore, you always divide by n. Okay? You always divide by n. 3, because I had 3. Make sense? Now, so that's the reason why sometimes we divide by n and sometimes we divide by n minus 1. Now, the notation helps you know what are you referring to. If you are dealing with the population, we use the letter sigma. So this is the variance of x. This is the standard deviation of my random variable x. If you are dealing with a sample, we use s squared. You know, standard starts with s. So s, this is sigma. S squared, that is the variance of x, just like that one, except that you divide by n minus 1. And this is the standard deviation of x. And as you can tell that these are not necessarily the same, right? Because when you divide by n minus 1, there is a difference, okay? So that takes me to the last idea. First, recognize that the variance, both the variance and the standard deviations are always greater or equal to 0. Why? Because the variance, it's the sum. These are either positive or 0, plus positive or 0, plus positive or 0. This is positive or 0. Divide by n, it's still positive or 0. Okay? So there is no question about the variance. When you take square roots of this quantity, this is also a misconception. And it comes from this idea. Students believe correctly that square roots of x squared is plus or minus x. This is correct, okay? This is correct. Because if x equals 4, we get 4 squared, which is 16. Square root of 16 is 4. So 4 produced 4, didn't it? As if I'm trying to say square root of x squared is x. That's true if x is positive. But if x is negative, if x is negative, let's look at it. Negative 4 squared is 16, sorry, and square root of 16 is still 4. So now negative 4 produced 4, which is minus negative 4. You either produce the value that you start with, or you produce the opposites of what you start with. Because we don't know what x stands for, we don't know if this x is 4 or negative 4, we have no choice. We have to say plus or minus x. But if you knew that x is positive, right? If you knew that this is positive, then you don't need to say plus or minus x. In other words, square root of 16, never say plus or minus 4. It's just 4, okay? You know, people make this mistake. They think it's plus or minus 4 because we know 16 is positive. Square root of 9 is 3. Never do this, okay? Never do this. This is wrong, okay? Think of square root function, okay? Here is 9. And it only produces 3, okay? But when we don't know what's in here, that's where we do the plus or minus x. That's why when I said, what is square root of x squared? You say plus or minus x, because we don't know the value of x. If x is positive, you're going to get x. But if x is negative, you're going to get negative x, which is also positive. I'll repeat. If x is negative, you're going to get negative x, which is positive. Let me ask you a different question, because I have seen this over and over and over again. See if you can answer this question. What's the sign of 4? Excuse me. What is the sign of 4? The sign of 4. Yeah, it's positive. No problem. What is the sign of negative x? What's the sign of negative x? What's the answer? We don't know. Don't let this negative deceive you. What's the sign of x? What is the sign of x? Sign of x. Don't know. Okay? So when I say, what's the sign of a negative x? I don't know. I really don't know. Because if x is positive, negative x is negative. But if x is negative, sorry, I'm messy. If x is positive, negative x will have to be negative. But if x is negative, negative x is positive. In any case, all of this is kind of irrelevant, except that I don't want to see the following. Never get when you take square root of this quantity, you will get a positive value. You're not going to say plus or minus x. In other words, don't do this. Don't say the variance. Don't say the square root of the variance is plus or minus the standard deviation. This is silly. Okay? It's just the standard deviation, and that standard deviation is positive. Just like if I say square root of 9, the answer is 3. Okay? Therefore, the square root of the variance is just the standard deviation. That's positive, and the variance is also positive. Or 0. Could be 0, but they cannot be negative. Last thing I want to say is this. What if you want to compute the variance or the standard deviation, actually just the standard deviation, on the calculator? Because as you can tell, if I have a lot of data points, it's very hard to do the math. So it's very simple. You'll go to your graphing calculator, go to stat edits, put your numbers under L1, go to stat calc. We did this before. You get one var stats. Go to down where it says calculate or enter, and you're going to get these numbers. This is how we get the 5 number summary. If you remember, if you scroll down, you're going to see the 5 number summary. You're going to see Q1 and Q2 and maximum and minimum and all that stuff. At the top here, you're going to see these numbers. This is clearly the mean, so you get that for free. And you could skip these for now. Don't worry about them for now. This is actually extremely useful. I'm going to show you another definition of the variance using this, okay? And then you'll see these two numbers. Well, that is the standard deviation if you're dealing with a sample, and this is the standard deviation if you are dealing with the entire population. And your calculator doesn't know. It'll give you both. You have to decide whether you should use this or this. So I would suggest you pick a set of data, like students' heights, and find the variance and the standard deviation, assuming 15 students in the class is the entire class, and see if you get this. And if you divide by n-1 instead of n, you're going to get this for sure, okay? And you will see that they are different, of course, all right? So that should end this video, and I will see you next time.